All right, so a little bit about me. So my name is Rohit Musti, and I work as a software engineer at American Forests. I build tools like the tree equity score, a couple of hobbies. I love to rock climb, and I've recently become an extremely enthusiastic but very much amateur bike mechanic at a free bike repair clinic in my area. A little bit of my teaching history. So I got my start as a teaching assistant for Introduction to Computer Science. I then taught a student-led class about spatial reasoning. So link there if you want to check that out at some point. Then I was the head teaching assistant of an algorithms class. Then I kind of designed my own teaching class again as a graduate student around some topic called digital governance. And most recently, I was a graduate teaching assistant on a class called Introduction to Cryptography. So this is not my first rodeo, and I have quite a bit of experience in this space. So I thought for this lecture, we'll go over a few things. We'll discuss some of the course goals, some of the class policies, and we'll also discuss some of the history of cryptography. If we've got enough time, I'd love to get into a little bit of a discussion about one-time pads to give you a flavor of what this class is going to be like. We're not going to get too deep into them, but we will definitely develop a surface level understanding. I'm hoping to keep this class around an hour to an hour and a half. That's the first day, and I'm kind of, giving everyone a flavor of what's happening. So with that, let's dive in. If you have any questions, I'm able to see the chat. So if you just message everyone in the chat or message me directly, I'll be able to see your question. And please feel free to ask questions and stop me if I'm reviewing something and it doesn't feel quite right to you. So with that, course goals. The course goal is to develop a strong foundation of cryptographic primitives. By cryptographic primitives, I mean tools like public key encryption or semantic security, these kind of basic building blocks of security. And the goal of developing these, the point of developing these strong foundations is so that you can, if you so wish, continue on to further academic study, whether that's in another course or graduate work, or you can continue to work into the field as a cybersecurity professional or contributing to open source cryptography projects. At the very least, I hope at the end of this class, you all feel very comfortable enthusiastically explaining cryptographic ideas to your friends and family over dinner. I know that's kind of how I got my start. So let's go through a few course policies. Any questions on that goal, by the way? Does anyone have any different goals from this? All right, we'll continue on. So course policies. First is the course contract. As the instructor, I am agreeing to provide you with the resources and ideas you need to succeed and thrive. As a student, I hope that you agree to do your best to achieve those goals in this class and follow all the course policies that I'm going to lay out. The course honor code, where I went to school, we had an honor code, and it was a really good system for many reasons, so I thought I'd try to have one for this class. It's pretty simple. It's basically don't lie, cheat, or steal. I want to develop a really trusting environment in this class. And I'm not going to be looking over your shoulder or scouring your papers for potential plagiarism or be trying to trip you up. Oh, we have a question. How do you think you as a software engineer have used cryptography in your career? That's a great question. I think we'll start with some of the basic reasoning skills you develop in this class. The ability to reason about security and cryptography and some of the probability and math behind it has been hugely instrumental in making me a better overall software engineer. I think specifically about the content of cryptography, the content of cryptography has helped me, one, implement security with login systems. I have a very deep understanding of basic encryptions. And so when I'm implementing them at work on a day-to-day basis, I understand what errors are serious errors that could endanger security and what errors are not as serious errors. However, for the most part, I'm not implementing the raw security libraries myself, but I am able to audit them. Does that help answer your question, Hilarion? Or I guess
Yes, thank you.
Yeah, sure thing. So back to the honor code. And thank you for the question. I appreciate you being the brave one. Yes, these recordings will be accessible to you outside of class. We'll get more to the policy and recording. I'm going to do my best to kind of, chop these up into smaller videos so that way you don't need to watch the entire thing at once. And so I'm going to do my best to make this available to you outside of class, Brar. Does that help you? Great. I'm seeing a smiley face. All right. So if there's any more questions, please put them in the chat. They're super great. If everyone asks a question today, I'm going to feel really successful. So the course honor code, yeah, I'm not going to be trying to trip you up and catch you, copying answers or anything like that. However, if you're feeling stressed about a potential assignment or about your grade, please reach out to me. Please don't make decisions out of desperation. You know, there's not some number of A's I'm trying to achieve, number of D's and number of C's. I'm hoping that everyone in this class is able to go the out of it. So if you're feeling stressed out, please reach out and try to avoid, any desperate decisions. It's all going to be, I'm going to give a lot of flexibility in my policies with the hope that no one feels any pressure to do anything like this. Any questions with the course honor code? I know that this is maybe a little bit unusual or not something you've seen before. So I'll give us a couple seconds to think about that. All right, seeing no questions, we'll move on, but if you have any questions later on that occur to you later, feel free to put them in the chat. Course attendance. So course attendance is not mandatory. And I'll do my best to record these lectures. We'll talk more about that later. So if you miss a lecture because you have an appointment or you have another obligation, please don't worry. And additionally, all the course slides and materials will be made available at least one day after the lecture. So if you want to refer back to the slides being used or any of the documents I reference, I'll make sure those are available to you so you have access to those. However, I strongly encourage attending and will do my best to make this lecture as entertaining and useful to encourage that. I'm also hoping to build in quite a bit of interaction in the class so you aren't just sitting there for 3 hours on Wednesday evenings while I talk at you. I'm sure you wouldn't find that very fun, and I know I would. I really enjoy the interaction. So course errors. If you find any mistake in the course website, slides, homeworks, any class materials that I'm producing, I will award you up to 5% extra credit on a given homework assignment. So what that means is, if you have a 97% average in the class, you won't move up to 102. Rather, any individual assignment you choose, I'll give you 5% more points on that assignment, up to 5% more points on that assignment. Additionally, I will award another 2% on top of the original credit if you actually make the pull request on the course GitHub repository to correct the problem. And if you want to learn more about GitHub or what that means, we can talk more about that later. And this is a first come, first serve policy. So if I make a spelling error and Jeremy spots it, and someone else is more interested and someone else sees it too, whichever one of you reports it to me first, we'll get the credit. Office hours. So these office hours are going to be by appointment. And so that's just going to be reaching out over email. Wouldn't it be a push request if you're pushing code? Great question, Abrar. So you will be pushing code to a branch or to your local repository. However, you'll need to make a request for me to pull your code into the main repository. So it would be a pull request. Office hours. So office hours, they'll be made by appointment. Please just email me directly. The reason for that is I have a full-time day job, and so I'm not able to reserve Fridays from 1 to 5 p.m. To be open and be online. However, if you just email me within a couple of days, I'll make sure we can talk face to face over office hours. I think office hours are really important, and when I was a student, they played a huge role in my ability to learn and in my ability to develop a relationship with the professor that I was working with. And so I will offer an additional 5 out of 5 assignment points to anyone who meets with me at least once on an assignment of their choosing. So what that looks like is if an assignment is worth 10 points or 100 points, and um, you get a 90, adding the 5 out of 5 would make the assignment worth 95 out of 105. It's not quite the same as a 5% bump, but I think hopefully a good incentive to get everyone excited about coming to office hours. I know that having them be set up over email is a barrier, so this is my way to hopefully reduce the barrier. Office hours also are not limited to just course content. You want to talk about topics like careers in software engineering, graduate school, or other struggles and stresses that are weighing you down. I hope to be a resource and someone you can talk to. Everything we talk about will be confidential, so I'm not going to do any external reporting on what's happening in office hours. Recording lectures. So I think this gets to your earlier question that came up. So as you all know, it feels a little bit uncomfortable to be recorded, especially by someone else. And so with that, please don't record me without my express written permission. I'm going to do my absolute best to record these lectures and post them online so you can kind of view them at whatever pace you want. However, I'm not going to, there's some barriers in the way of that. It'll take me a few hours to make those edits. So if you have a special accommodation or you just need it for note taking for a specific reason, just let me know and we'll be able to work it out so you can be able to take notes in the class. Any questions on these course policies? I'm looking at the chat and not seeing any right now. But I'll take a beat because I know I went through a lot. So just to kind of recap, we talked about the course contract, the course honor code, the policy on if I see an error in the class, and also talked about recording lectures. All right. Homework and grade policies. So let's start with the course grade structure. I know this is always a big priority for me when I was taking classes. So this is the first option on how we'll calculate your grade. It will be the sum of the points you earned on the various homework assignments divided by the sum of the total possible points on the homework assignments. The second option is the homework points will be worth 75% of your overall grade, and the final exam score will be worth 25% of your final grade. So the reason I'm offering these two options is I want everyone to be able to express their abilities the best way they can. And for some people, the stress of final exams is too much and they're not able to perform their best in that environment. So in that case, I hope the homeworks are a way for you to express your knowledge. And for other people, the endless time being spent on a single assignment can be a little stressful, and they often prefer exams. And so I hope that no matter who you are, you have an option on how you want to be graded. And you'll have to decide on which of these two options you want to pursue sometime in late March, simply so that I can make the final exam. What we're not going to do is you do all the homework, you take the final exam, and you pick whichever one's higher. So there's the flexibility. Any questions on how this works? All right, not hearing anything. We'll keep moving through it. So late homework. So in general, homework needs to be submitted on time, and I'll aim for about one homework assignment every 2 weeks. However, something I'm going to offer is 5 total late days throughout the semester, with a maximum of 3 late days applied to a single assignment. So if homework is due on a Tuesday and you submit it on a Wednesday, that's using 1 late day. If you submit it on a Thursday, that'd be using 2 late days. And when we're noting late days are whole days. So if an assignment is due at 5 p.m. and you submit it at 6 p.m., you'd be using 1 entire late day. The same as if you submitted it at 4 p.m. The day after. So I hope this adds some flexibility, so that way if life gets in the way and you're not able to work in a certain space, you've got that option. Dropped assignment. So you'll be allowed to drop 1 homework assignment from your overall grade. Now, there may be 1 or 2 undroppable assignments. However, I will label them very clearly when I assign them, and I will make it very obvious that that's not something you can drop. This is just so that if you have a bad day, it doesn't get in your way of being able to get the grade you want in this class. Extra credit. So again, if your grade is not as high as you would like it to be, we can have a one-on-one conversation about adding an additional assignment to the overall course. What we'll do is we'll pick a topic in the course you find interesting, and then I will design an assignment around it. Then I will make that assignment extra credit available to the entire class. In general, there's not going to be too many of these. However, I'm going to hopefully be able to add them so that way, if you're not where you're comfortable at, then you've got the space you need to make up ground. Miscellaneous. If you try to hack any grading system or any test cases I set up, you will immediately fail the class. This is just because it's dangerous for the computers, and it kind of violates the honor code too. So please don't try to do it. Also, collaboration is allowed in assignments, but everyone who's collaborating will need to list who they are collaborating with on their assignment and briefly describe about 1 to 2 sentences on the sections you collaborated on and kind of the nature of the collaboration. Now, let's pause a minute and talk about collaboration, because it's different than cheating. Collaboration is not, you do questions 1 through 3, I do questions 4, 5, and 6, and then we compare and copy and paste. That's not what collaboration is. Collaboration is working on, tough parts of the question together, and collaboration is also discussing things on a blackboard or a whiteboard with one another. So, in the real world, you're allowed to collaborate, so you are in this class as well. However, in the real world, you're also, responsible for not misrepresenting which work you've done. And the same is true in this class. So that concludes the discussion of the course policies. Any questions or anything? Things felt like they've been quite clear, but I want to give everyone some space and some time to just think about that for just 1 minute. So I'm going to wait until 5:55 to discuss it, to give you time. Actually, let's take a break until 6 p.m. It's 5:54 now. Everyone, take 5 minutes, go to the washroom, drink some water, do whatever you need to do, and then we'll come back at 6, and we'll discuss an overview of cryptography and the history of cryptography and one-time pads. So thank you, and we'll take that 5-minute break now. I'll see you at 6 p.m. All right. 6 p.m. and we're back. There was one question I received during the break, and it was a question on what kind of assignments can we expect in this class. And with that, so cryptography is traditionally a mix of mathematical proofs and those are typically handwritten or through PDF submission. And there will also be some programming assignments. I'm still deciding the exact balance between programming assignments and handwritten proofs. However, there will be at least 1 or 2 programming assignments and at least 1 or 2 proof-based assignments. Any questions on the kind of what that means, what I mean by proof, what I mean by programming assignment, anything like that? As far as programming languages on the assignments, that'll likely depend on the assignment itself. I'm personally a huge fan of Python. However, some of its properties make it difficult for cryptography use. As opposed to more programming assignments, I hear you. One of kind of the golden rules of cryptography is to avoid implementing your own security. And so that kind of makes it difficult to design assignments around it. That being said, we absolutely will have a few. So we'll definitely have some space for that. And I think you'll have a lot of fun with the handwritten ones. I was surprised at how much I enjoyed them. All right, so with that, an overview of cryptography. I require these proofs to be extremely rigorous and precise. I will require precision on these assignments, and I will require some level of rigor. However, this is not a graduate course, so I will adjust my expectations, and I will also give you. By the time you receive the assignment, you will have seen many proofs in class, and I'm going to hold you to the standard that I hold myself to during class. And so don't feel stressed that, and if a proof is not rigorous enough, I will make it, I will give you the opportunity to make it more rigorous, to demonstrate your knowledge there. And if you are in the middle of an assignment and you're wondering if it is rigorous enough, we can talk about that on a case-by-case basis, but please don't worry too much about the rigor and exactness of the proof. You're not submitting papers to a research convention or anything like that, so I'm not going to hold you to that standard. Any other questions on the proofs/programming assignments? All right, not seeing any. I'm going to continue on, but if you have a question later in the lecture, please feel free to ask. And in all of the lectures, I'm going to be including these kind of 5-minute breaks. I know that this is a busy time in the evening, and many of you have other obligations, so I don't want to take away from that. All right, so overview of cryptography. So I guess the bigger question, what is cryptography? So let's take an example where we have 2 protagonists, Alice and Bob. Alice wants to send Bob a message, but she has to pass the message through an unsafe medium. You can think of this like you were in class and you've written a note and you want to pass it to your friend. However, to pass it to your friend, you need to pass it to someone else who will then pass it on to your friend. You don't want that someone else, we'll call them Eve, eavesdropping on your message. So the kind of aim of cryptography is to provide Alice with the cryptographic primitives, aka tools necessary, so that way she can encrypt her messages. So there be a couple of requirements. First, that no one can eavesdrop on her communication with Bob. This means no one can see the message and then take the message and learn something about what she was trying to say to Bob. The second requirement is that no one can tamper with the communication. This needs to be such that whoever receives the note can verify that the note was not tampered with. So this leads us to a definition. Cryptography is a study of secure communication through untrusted mediums. So let's talk about some applications. The first is digital signatures. Digital signatures are a tool you can use to sign digital documents. You can think of them as an analog to physical signatures. If I write you a letter and I physically sign it, you can't copy and paste that signature to another document. You can't exactly copy it. And you also have this property that they're not transferable, right? If I sign one document, that doesn't mean I signed another document. So digital signatures are a byproduct of some cryptographic primitives that we'll discuss throughout the class. Anonymous communication. This is an extremely important application. Let's say you wanted to make an anonymous complaint about the class. Well, I as the lecturer of the class want to know that it is a student of the class making the complaint, but I'm not that interested in which specific student is making the complaint. With cryptographic primitives, you can, through layers of something called a mixnet, you can encrypt and decrypt the communication such that I have no idea who the message came from. All I know is that what the message contents are, and that the message was written by someone in the class. Another example is multi-party computation. So multi-party computation is we all hold one piece of a larger data set, and we want to do some computation on that data set. Let's say we all know our grades in this class, and we want to find the class average. What multi-party computation allows us to do is provide the answer to that computation without any trusted actors, right? The kind of basic model is we all hand our grades to a trusted person or trusted service, and that service or person makes the calculation and provides it back to us. However, if we don't trust one another, cryptography allows us to develop tools that allow us to mathematically trust one another, even if we're still building that trust with one another. Another example is anonymous cash, anonymous digital cash, I should say. So if you walk into a bookstore, Abrar, isn't your example single party? So I was offering the example of the trusted individual as an example of what is an example of the problem multi-party computation is trying to get around. So multi-party computation is several people coming together and performing that computation through a series of messages they exchange collectively. So does that answer your question, Abrar, or do I need to go through that example again? Great. Okay. Anonymous digital cash. So anonymous digital cash, if you go to a bookstore and you buy a book and you pay $5 for the book, the person who sold you the book doesn't necessarily know who you are. All they know is that you had $5 and you left with the book. With digital transactions, there is a similar cryptographic protocol we can have in place where someone can digitally buy a book, and to the seller, it just looks like cash. It doesn't look like they actually get any information about the individual person. So, in the world of this is not cryptocurrencies. This is different than that. This is an example of how you can use cryptographic primitives to obscure the source of the cash. And if the person tried to spend money again somewhere else, and they tried to spend the same dollar, they wouldn't be able to spend the same digital dollar. Private computation on untrusted hardware. Let's say you wanted to perform some math on some very sensitive data, maybe health records, and you didn't trust the provider of the computer you were using to make it to do the computation. Wouldn't it be cool if you could not trust the hardware, but still actually make the computation? And cryptography has some pretty magical properties that allow for that to happen. And lastly, zero knowledge systems. These are ways of confirming information without necessarily revealing the information. This is personally my favorite part of cryptography. An example of a zero knowledge system is if you had the book Where's Waldo and you wanted to prove to me that you knew where Waldo is, but you didn't necessarily want to reveal the location of Waldo in the book to me. What you could do is you could take a really big sheet of paper that's, 4 or 5 times larger than the book, poke a hole in that sheet of paper, and place that hole over Waldo. And then I wouldn't know, where in the book that particular Waldo was. All I would know is that within the book, you can locate Waldo. And there are many, many more. Any questions on some of these broad ideas on what cryptography is or its applications? I'll give it 1 minute so you can kind of think for a second. I went through a lot of complicated examples. I want to make sure that everyone feels like they understand them. All right, not hearing any questions. We'll keep going. So with that, let's go through a quick history of cryptography. This will not be exhaustive, but I hope it gives you some context on, what we're studying within the course of history and some of what came before us. So the earliest kind of arguable example of cryptography is hieroglyphics in around 1900 BC. So what would happen is that kings and their scribes would write messages in hieroglyphics that would be only known to them. What are some flaws in hieroglyphics? What do you guys think? Are there any flaws to the system of hiding information? The system being writing messages in some strange symbols. So James, you said leaks. Do you mind messaging a little bit more about what you mean by leaks? Also, feel free to speak aloud if you prefer that to typing. Yeah, that's a great example, James. If someone learns cryptography or learns the language, you can catch it. And Japan, easy to decipher. Absolutely, they're literally pictures. Or rouge. If you use the same symbol over and over, people can figure out what they mean. That's called a frequency analysis attack. And we'll actually discuss that later on. So great intuition, Rouge. Yeah, so I think y'all really got there. Mariglen, recognizable patterns, absolutely. So yeah, anyone who learned this quote unquote code could read the message plain as day. This is like a modern day equivalent to writing a message in Arabic and just hoping that nobody around you can read it. So we're going to fast forward 1700 years, and that brings us out. The audio is a little bit muddy. Let me double check. The audio sounds okay to me, but okay. Larry, and I'll try to do a couple of checks myself after class, but thank you for bringing that to my attention. That might not be perfect. Thank you. Okay, so the Caesar cipher. The Caesar cipher is created by Caesar and his generals to communicate knowledge. We don't actually know if Julius Caesar came up with the cipher, but it's commonly attributed to him. Essentially, you just shift the letters or numbers over by 3 characters. So if the letter is A, you shift it over to D, because D is 3 letters away from A. So here's a little small example of how you might code a Caesar cipher. First, we have the alphabet, A, B, C, all the way through until Z. Then we have the secret, hello, and the number we're shifting by, 3. Caesar often used 3, and so the most classic Caesar cipher is shifted over by 3. However, there are other ciphers that are essentially Caesar cipher, but they have a variable shift. So with that, that's a setup. Here's how you encode the message. So given a plain secret and a shift amount, for every letter in the plain secret, you find that letter's index in the alphabet. Then you add the letter that comes 3 after that current letter, and you use mod by 26, since 26 is on the line of the alphabet, you want the alphabet to wrap around. Next, you decode the message. So to decode the message, you take the encrypted secret and the shift, and it's very similar to the original process. However, instead of shifting forward, you shift backwards. And on line 16, I see that I made a small mistake. Instead of doing mod 26 at the end, it would be the current index minus 3. And if that number is negative, then it would be 26 minus that negative number. So I got that mistake. It's not eligible for extra credit, but that's the kind of mistake you might catch that would be eligible for extra credit. All right, any flaws in the Caesar cipher? Open to the class. Key is easy to find. Thank you, Andrew. David, the letter frequency, exactly. Jared Mitchell, brute force. Yeah, there's like 26 options. Y'all got there really quick. Nice job. So yeah, what Jared said and what Andrew said, the key is very easy to find. There are only 26 possible keys, right? So very easy to brute force. A common flaw is that in hieroglyphics and this system is that they rely on secrecy of the system, not necessarily secrecy of the keys. It'd be better if even if someone else was aware of the system, they wouldn't be able to break it so easily. So great job, everyone, finding those flaws. So that brings us forward to the VIGENERE cipher. I might be pronouncing that wrong, but it came about 1,500 years later again, so like another almost 1,000 years. And this is the first cipher to use what we would consider to be a key or a password. This is essentially Caesar cipher, but with a longer key. And the key must be less than the length of the message. If the key is as long as the message, then it becomes a one-time pad, which is a different kind of cipher that we'll discuss later. So here's an example of the VIGENERE cipher. I gave them the alphabet, A, B, C, all the way through Z, and we have a key. In this case, the key is ABC, but it can be any length, and the secret message hello to encode. So the way this cipher works is you find the shifts, the amount of shifts required for every letter in this key. Now, since the secret is longer than the key will become ABCAB instead of just ABC to match the length of the secret, which is hello. Then for every letter in the secret, you find its shift total. This should be shifts, not shift. Let me make that correction. Great. So for every shift, for every letter in the secret, you find the corresponding shift, and then you set the current, and then you find the current index of the current letter, and then you shift the current letter by the shift amount. To decode, it's a similar process. You find all the shifts, you find the current letter's index, and then you shift it backwards by the shift amount. Any flaws in the cipher system? Yeah, great observation, Jared and Andrew. Brute force is another attack here. Brute force is a little harder here, but definitely doable. And frequency analysis is absolutely applicable. Andrew, same as Caesar, those are definitely similar weaknesses. So one flaw is if we knew the key length, we could break it using something as frequency analysis. We'll get more into that in a future lecture. But the basic idea is, knowing the frequency of certain letters that will map onto other kinds of frequencies. Similarly, if we didn't know the key length, we can break it by just trying all the key lengths with the random approach. Then we'll fast forward to the Enigma machine. This is, I believe, a World War II era security measure. Everyone was trying to crack the secret codes of the Nazis. And so this machine is very similar to other substitution ciphers. However, instead of using a phrase or a letter, it uses a series of rotating rotors. Now, this is ultimately vulnerable to frequency analysis. And that brings us to modern cryptography. So modern cryptography are primitives like the one-time pad, which we'll discuss in a moment. Symmetric key cryptography. This is where we have symmetrical keys and use those to encrypt and decrypt information. Public-private key cryptography. This is cryptography like RSA, something you should all hopefully be somewhat familiar with. Zero-knowledge proofs, as I discussed earlier, and multi-party computation. Let's talk a little bit about one-time pads, but first, any questions on this kind of previous cryptographic primitives we found? No? Great. So with that, let's talk about the one-time pad mechanism. So the way a one-time pad works, let's think of it as a VIGENERE cipher with a key that is as long as the message. So in this case, the key is a collection of bits 0 to 1 of length n. The message is a series of bits of length n that is also 0 and 1. And the encrypted message is a series of bits from 0 to 1 as n. The message is the key exclusive OR with the encrypted message, and the encrypted message is the key exclusive OR with the original message. Exclusive OR is the operation that is given 2 bits 0 and 0. Since they're the same bit, it'll return false. Given 0 and 1, since they're opposite bits, it'll return true. Any questions on the one-time pad mechanism? Yes, Abrar. One-time pad is very similar to masking. Very similar to bit masking. Would the number of key possibilities be 2 to the n? Yes, that is true, Daniel. Also, the number of message possibilities. The message space and the key space are the same here. That's a great observation. Great, we'll continue on. So let's talk about the security properties of one-time pads. And this is really kind of the meat of the course. So if you like talking about security properties, you're really gonna enjoy this class. If you don't, then you may not enjoy this class as much. So given a ciphertext, an adversarial attacker will learn nothing about the original message. This is the definition we're going to use to define security. Let's take it back to our example with Alice and Bob. If Alice passed a note to Eve, and then Eve were to pass the note on to Bob, that note would only be secure if Eve, upon trying to read the note, learned nothing about the message. And hopefully I can prove to you that the one-time pad meets that requirement. These definitions are extremely important. Early cryptography relied on intuition, but intuition isn't complete. Intuition does not provide mathematical guarantees we can rely upon. Intuition is also very limited. Just because I'm not able to find a way around a problem does not mean no one is able to find a way around a problem. And so since about the 1970s, we have moved on past intuition, and now we are in the space of using mathematical proofs. And the goal is to say, kind of the goal of cryptography is, given a message, an encrypted message, if somebody can break it, if someone can crack that message or learn something about it, that needs to be as hard as a NP hard problem or a known to be hard problem. And so by constructing our security systems in this way, we make it so that breaking security is as hard as doing something that we know to be not solved today. So let's translate this definition to something a little bit more mathematical. Given a ciphertext C, the probability that it is the encryption of any two messages M is equally likely. So I hope I've convinced you on the security of one-time pads. Let's talk about some of the weaknesses. Are there any weaknesses any of you see in one-time pads right now? Yeah, great point, Jared. If you reuse keys or you reuse messages, we'll get to that explanation in a moment, but you can actually break the security of a one-time pad. Are there any other weaknesses anyone sees? Mathematically derived? That's not so much a weakness at this point, James. That will lead us to a weakness to a different kind of weakness, but not in and of it. Being mathematically derived in and of itself is not necessarily a weakness. But great thought. All right, we'll start to go through some of the weaknesses. So one weakness is that the key can only be used once. As you can imagine, this is rather impractical for day-to-day use. So the reason that doesn't work is if you use the same pad on two messages and then apply the exclusive order to those two messages together, you then learn the exclusive order of those two messages, and therefore you've learned something about those messages. Now, next lecture, I'll show you why this weakness is so serious. Another problem is there's no integrity to a one-time pad encryption. What does integrity mean? Integrity means there's no way to know that the message you decrypt is the message from the original sender. The way you break integrity is just applying another, if you have an encrypted text, you can just apply another random key to it. And there's no way for the receiver to know that was tampered with. Are there any questions on one-time pads?